Now let's go to the second example. Now in this example we want to evaluate double integral of yz over the surface S, and this time your surface S is the upper half of a sphere of radius 2. Okay, now so the equation for sphere with radius 2 is x squared plus y squared plus c squared equals to 2 squared. But now we consider only the upper half of the sphere. So let's find its equation. To get that equation, first we need to solve for c squared. C squared equals to 4 minus x squared minus y squared. Therefore, c equals to plus or minus square root of 4 minus x squared minus y squared. Now, since we consider only the upper half, where the c values are positive, we should consider the plus sign. So now the equation of the upper half of the sphere should be square root of 4 minus x squared minus y squared. So this is your surface S. Now, as always, let me draw the picture. XYZ. Now we have the upper half of the sphere. So surface S should be this part. That's your surface S. Yes, and its equation is C equals to square root of 4 minus x squared minus y squared. Now on this surface, we have our function g, which equals to y times c. Okay. Let's integrate this. So double integral of y times c over the surface S equals to double integral of y times, now what is c? Now c values are given by the c coordinate of the surface, which equals to square root of 4 minus x squared minus y squared. What is ds? ds equals to square root of 1 plus partial f of partial x squared plus partial f of partial y squared dA over the domain D. Now, okay, so on the surface we have ds. On the domain D we have this dA. Okay, now, as you can see, to represent a surface, I always use big S. Now, in line integrals, I use little s. Okay. So next step is to calculate these two quantities, f sub x and f sub y. So let's do that. We know that c equals to square root of 4 minus x squared minus y squared. We can think this as 4 minus x squared minus y squared to the power 1/2. This is your f. Therefore, partial f of partial x equals to 1 half times 4 minus x squared minus y squared to the power negative 1 half times negative 2x, and partial f of partial y equals to the same thing, except now we have, instead of negative 2x, we have negative 2y. Here I use the chain rule to calculate these two partial derivatives. So this is something like big x to the power n. So we have n times big x to the power n minus 1, and here your n equals to 1 half. So basically I have 1 half times this quantity time to the power negative 1 half. 1 half minus 1 is negative 1 half. And then we have to integrate, or we need to use the chain rule. So we need to integrate this quantity with respect to the x variable. And if you do that, you will get negative 2y. And we use the same recipe to get partial f of partial y. Then we will get this expression. I think we can cancel this 2 with this one. Okay, and those are the two partial derivatives. Okay, let's substitute these two partial derivatives into the equation. Y times square root of 4 minus x squared minus y squared times square root of 1 plus partial f of partial x equals to, so you have negative x over square root of 4 minus x squared minus y squared. Since this is a negative power, we can take it to the denominator with the positive power. We should square this quantity plus negative y over square root of 4 minus x squared minus y squared to the power 2 times dA. Now if you simplify the integrand, you will get y times square root of 4 minus x squared minus y squared 1 plus x squared over 4 minus x squared minus y squared plus y squared over 4 minus x squared minus y squared dA. Now let me simplify this, the quantity under this radical sign. So the common denominator should be 4 minus x squared minus y squared. If you do that, you will get 4 minus x squared minus y squared plus x squared plus y squared all over square root of 4 minus x squared minus y squared dA. We can simplify this numerator. So basically you will get square root of 4 over 4 minus x squared minus y squared, which is same as 2 over square root of 4 minus x squared minus y squared and as you can see, now we can cancel this term with this one. So basically we want to integrate 2y over the domain D. Now your domain D is on the xy plane. So let's consider the shape of this domain D. Now if you look from the top, you will see the projection of this surface S on the xy plane, and your domain D should be a circle with radius 2, because on the xy plane your c coordinate equals to 0, and you will get the equation of a circle with radius 2. Circle with radius 2, so it should be x squared plus y squared equals to 2 squared. You can get the same equation by substituting c equals to 0 into this equation. This is x squared plus y squared equals to 2 squared. Now we need to solve this double integral. I think it is easy to use the polar coordinates to solve this double integral, because my domain is the boundary of the domain is a circle with radius 2. So then this double integral 2y dA becomes, okay, now in polar coordinate system y value is given by r sine theta. Area element dA equals to r dr d theta. R goes from 0 to 2, and theta goes from 0 to 2 pi. Okay, let's integrate this. We can pull out 2 from the two integral signs. And if you simplify the integrand, you will get r squared sine theta dr d theta. My first variable of integration is r, so we can treat sine theta as a constant. Integrate r squared, you will get r cubed over 3. Lower limit is 0, upper limit is 2 sine theta d theta. Apply the upper limit first. You will get 2 to the power 3 over 3 minus the lower limit is 0, so you will get 0 d theta. 2 to the power 3 is 8, so we have 8 over 3, which is a constant, and 8 over 3 times this 2 becomes 16 over 3 sine integral of sine theta d theta. Now if you integrate sine theta, you should get minus cosine theta let's apply the upper limit first. You will get minus cosine 2 pi minus cosine 0. Cosine 2 pi is 1, so we have negative 1 minus times that minus becomes positive, and cosine 0 is 1. This. Now as you can see, this surface integral becomes 0. With this, I finished the second example. And next, we are going to consider the surface integral of a vector field.